Unit 2, Logical, Connectives, and Quantifiers. In order to make compound propositions, we need to define logical connectives. In order to specify quantities of variables, we need to define logical quantifiers. The following is a form of first-order logic. Connectives are part of predicate calculus, but quantifiers are not. So you have to go up to first-order logic, which also includes quantifiers as well. So first-order logic is the main logic that we'll use and that is used in a lot of mathematics. There's second-order or higher-order logic as well, and you don't need that for a lot of stuff. So, okay, logical connectives. A proposition can be either true, denoted by this T-looking thing, and false. In LaTeX, true is top, and false is bot. Just a little FYI, top and bot. When it does not combine a logical connective, or does not contain a logical connective, this proposition, it is called an atomistic proposition. To combine propositions into a compound proposition, we require logical connectives. They are not, which has that symbol as its notation, and, which has that symbol, and or, which has that symbol. Table 2.1 is a truth table for a number of connectives. So let's look at this truth table. Who has seen a truth table before? Okay, you all have. That's good news. That means that it's going to be super easy for you to do this. Okay.
In embedded computing class.
Yeah, in embedded computing we did the truth table, didn't we? In embedded computing we also looked at logic gates. But we're not going to look at logic gates in this class because we're just very into just the math aspect. Although logic gates do these operations, right? So how to make a physical thing act as one of these logical operators is what those logic gates do in circuits. So in digital circuits. Okay, so the first two columns of this table are truth values of propositions P and Q. And the rest are output. And then what we can do is we can use these connectives to make compound logical propositions, compound propositions. Okay? So proposition P in this first row is false, and proposition Q is also false. And in the second row, we have proposition P being false and Q being true. And then in the third row, we have P being true and Q being false. And then finally, we have in the fourth row, P and Q both true. Okay? So we're going to look at what happens when we use these logical connectives for each of these cases, going by row. So let's look at what happens with not. We only have one connective that's a connective with itself, right? And so P is just the opposite truth value. So not P is the opposite truth value of P. So if we have P being false, then not P is true. If we have P being false, then not P is true. If we have P being true, then not P is false. If we have P being false, then not P is false. So it just flips that bit, right? Okay. The rest of them have a combination of P and Q. So and. So P and Q is false when both P and Q are false. When P is true when P is false and Q is true, and P and Q is also false. When P is true and Q is false, and is false. So it has to be both. They both have to be true, right? So P and Q both true, evaluates to true. Or, is the next one. So P or Q. So if they're both false, P or Q is false. If one of them, at least one of them is true, then or comes out to be true. So when P is true, or when P is false, Q is true. P or Q is true. When P is true, Q is false. P or Q is true. When P is true and Q is true, P or Q is still true. Okay? Now we have the weird ones that we don't use as frequently, but you see a lot of times when you look at logic gates. So NAND, NOR, XOR, and XNOR. And these can essentially be thought of as deriving from the fact that we started drawing truth tables, and we were like, oh, hey, we have all these other possibilities, right? We could make some other connectives that have different logical outcomes. So NAND is essentially the opposite of AND. It's not AND. It's equivalent to taking AND and then doing not on the whole thing. So if you look at AND, it's false, 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 true. NAND is true, 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 false. NAND. Okay. NOR is essentially a not or. Okay, so if you look at or and you see it as false, true, 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 NOR is true, false, false, false. It's not or. Now we got the X ones. XOR is false, true, true, false. Okay, and essentially they call it exclusive OR. It's OR, so the first three are the same as OR, right? False, true, true, false, true, true. But XOR requires it to be only OR, not AND. You can't have both being true. If both are true, XOR gives you false. Okay? Exclusive OR. Exclusive NOR, yeah, it's the exclusive. It's the opposite of exclusive OR. Okay, so it could be NEXOR, but it's called XNOR, and it's the opposite of this. So when they're both the same, okay, both false or both true, this comes out to be true. If they're different, then it comes out to be false. And that's XNOR. Okay. Cool. Truth tables are really useful, especially if you start to get confused about things. It's got all the answers in it. Okay? Yeah, so truth tables, pretty great things. And those are, I mean, realistically, the first three columns, not, and or, are the ones that are the most important. The others show up mostly in doing Boolean logic gate stuff, which can be useful in some situations, but they're not going to show up all over the place. You're going to see a lot of mathematical statements with an XNOR showing up in there. If so, it's probably written by an electrical engineer. Okay, quantifiers. Logical quantifiers allow us to indicate the quantity of a variable. The universal quantifier symbol, given by this V with a line through it, means for all. For instance, let A be a set. Then for all A in A, means for all elements in A, and gives this quantity variable A. So it's saying A ranges over, little a ranges over the entire set, big A. The existential quantifier, it's the backwards E, means there exists at least one, or for some. Okay? So for instance, let A be a set. Then there exists A in A means there exists at least one element A in the set A. Okay. And those are the two most important quantifiers, and so I thought I would mention them. They show up pretty frequently, so it's worth using that, especially the for all or the for each universal quantifier symbol. That one shows up a lot. So okay, so these are the basics of logic, of first order logic, and obviously they have applications in pretty much any sort of mathematical reasoning. If you want to say something's true, something's false, you want to evaluate whether a complex or a compound proposition is true or false, you can use these logical connectives and their and quantifiers to make statements, to make propositions, compound propositions. Okay? Okay. That's the basics of that. You can rewrite, by the way, I'm not going to do it, but you can rewrite the axioms of ZFC in first order logic. So you can rewrite all those axioms as being just like an expression where like for all and exists and all that. It's a little hard to parse when you look at it, honestly, but it's a little bit more precise of language. So if you want to make sure that somebody understands what you're meaning, you can use this. And you're going to see this stuff, so it's nice to be able to interpret these statements when you see them. Okay. Any questions on logic? Okay.